All right, on page 161 of your notes packet, we're looking at the second part of 7.2, still working with matrices. So we're going to start off with an example of an application using one of the operations that we talked about in the last part of this section. So we have a florist making flower arrangements. There are 3 different arrangements that the florist is making, and each arrangement is made up of roses, carnations, and lilies. And the florist has 2 different places where she can buy or he could buy the flowers. So what we want to know is we want to know the cost of making each of the flower arrangements from each of the wholesalers. So our goal is to have arrangement 1, 2, and 3 from wholesaler 1 and wholesaler 2. So we kind of want a 3 by 2 matrix, okay? So if we look at what we have, right now, what we have is the types of flowers by arrangements and the types of flowers by wholesaler. But in order to get my arrangements by wholesalers, we'll have to change matrix 1, okay? So we can rewrite matrix A as its transpose. Now what that means is we're rotating it. We will rotate matrix A. Okay, so if you look at matrix A, right now it's flowers by arrangement, and we're going to rewrite it as A transpose, which is arrangements by flowers. And I'm using the abbreviations for the flowers. So in arrangement 1, we have 5 roses, 6 carnations, and 4 lilies. In arrangement 2, we have 8 roses, 6 carnations, and 3 lilies. And in arrangement 3, we have 7 roses, 7 carnations, and 3 lilies. So I've taken the same information from matrix 1, but I've written it in a different way so that what we can do is find A transpose times matrix B, which will then give us our desired matrix, which is the arrangements and the wholesalers. So rewriting A transpose 5, 6, 4, 8, 6, 3, 7, 7, 3 times B, which is 1.5, 0.95, 1.3, 1.35, 1.00, these are prices, 1.35. Okay, and remember, when we're multiplying matrices, you have to do across and down. So we would take I'm going to do the scratch work on the side. So 5 times 1.5 plus 6 times 0.95 plus 4 times 1.3. Put that into a calculator and you'll find 18.40. Doing that for each of our elements, now we had 3 by 3, okay, and 3 by 3, 3 by 3, and then you'll do the same thing for the second column. Each of those 3 times the column, and you'll end up with a 3 by 2 matrix, okay, and our resulting matrix should be $18.40, $18.15, $21.60, $20.85, $21.05, and lastly $20.50. So this is our 3 arrangements from wholesaler 1 and wholesaler 2. All right, on the next page, we're looking at a special type of matrix. It's called the identity matrix. And just like with our previous, like with whole numbers and things like that, our identity is the element that is going to not change. So, for example, the multiplicative identity of numbers is 1, because when you multiply anything by 1, it doesn't change. Okay, and the additive identity is 0, because when you add anything to 0, it doesn't change. So we're looking at what type of matrix does this function of identity. Okay, and the answer is that it has 1s on its diagonal. So it has to be a square matrix. A square matrix, meaning 3 by 3, 4 by 4, 2 by 2, 18 by 18. As long as the number of columns matches the number of rows, and it has 1s on the diagonal from left to right, and 0s everywhere else. So we can say the identity matrix of n by n equals 1, 0, 0, 0, all the way out to our nth element, 0, 1, 0, 0, all the way out, 0, 0, 1, 0, all the way out. And then we can go down, we skip down to our nth row, and we have 0, 0, 0, 0, all the way out, and finally 1. So if you'll see, the 1s make a diagonal. Okay, and some examples of these, the 2 by 2, so I2 would be 1, 0, 0, 1. 2 by 2, right? 2 rows and 2 columns with 1s in the diagonal. I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. All 0s except for 1s on the diagonal. I4 would be 1, 2, 3, 4. Like so. All 0s except for 1 on the 1s on the diagonal. Okay, so what's special about the multiplicative identity is, by definition, identity means it doesn't change. So if I have matrix A, and it's an n by n matrix, then I could take A times the nth identity matrix, and that's the same as taking the identity matrix times A, and it would give me matrix A back. Now, this commutative of multiplication does not always work for matrices. This is the first time that we've seen commuting matrices here, and that's because usually it does not work. Okay, so be very careful of that. Now, another way that we see identity matrices is when we're looking at inverses. So an inverse matrix is another type of matrix. And this value here, AD minus BC, is called the determinant. And this is a very important value, AD minus BC, and we'll talk about it a little bit more in just a minute. Okay, so our goal here is to verify that matrices are inverses and to find inverses of matrices. So then we also need to know how to evaluate determinants. So let's start with a 2 by 2 matrix. And in order to find the inverse of a 2 by 2 matrix, let's just say we have matrix A, which is A, B, C, D. Then in order to find A inverse, we're going to take 1 divided by the determinant, which is why it can't be 0, times A and D switch places, and then we take the negative of B and negative of C. Okay, so an example of this would be if I have A equals 3, 1, 4, 2. I need to check AD minus BC equals 3 times 2 is 6, minus 4 times 1 is 4, is 2, which is not 0. So then I know that there's an inverse matrix. So to find the inverse matrix, I take 1 divided by, and I just found that it was 2, times 2 and 3 switch places, -1 and -4. So I end up with half times 2 is 1, half times -1 is -1/2. -4 divided by 2 is -2, and 3 halves. So this would be my resulting inverse matrix. Okay, now only square matrices have determinants and only square matrices have inverses. In general, the role of an inverse matrix is that A times B equals B times A equals the identity matrix. Okay, this is another of those rare cases where the multiplication of the matrices does commute. Okay, and if these two matrices are inverses, then we can say that B equals A inverse. Okay, not A to the -1. It's not raising it to an exponent. We haven't talked about what that would look like, a matrix raised to an exponent. However, in this case, we're not talking about like dividing it 1 by a matrix. We're talking about its inverse matrix. So looking at example 3 on the next page, we want to know if A and B are inverses. So first thing is to check their order is 2 by 2. Both matrices have an order of 2 by 2. So they're square matrices, so they can be inverses, and they have the same order. Okay, so what we want to try is A times B and see if it gives us the identity matrix. So I take 3, -2, -1, 1 times 1, 2, 1, 3. And again, we have to use our T method for multiplication. So we have 3 times 1 is 3, plus -2 times 1 is -2, which equals 1. And then T across to the second column. So 3 times 2 is 6. -2 times 3 is -6, which gives us 0. And then our next row, -1 times 1 is -1. -1 times, or +1 times 1 is 1, so that gives us 0. And lastly, 2 times -1 is -2, plus 3 times 1 is 3, which gives us 1. So this gives us 1, 0, 0, 1, which is in fact our identity matrix of size 2. Our order was 2 by 2, so yes, A equals B inverse, and B equals A inverse. The matrices will be inverses of each other. For example 4, we want to prove that its matrix A is singular. That means that it doesn't have an inverse. So let's go ahead and try to find its inverse. Remember, in order to find its inverse, we need to find the determinant. So the determinant of A was AD minus BC, which would be 6 times 1 minus 2 times 3, or 3 times 2, which is 6 minus 6, which is 0. And the determinant of A equals 0 means there is no inverse, because we would end up with 1 divided by 0. Example 5 is very similar to example 4. First, you're going to find the determinant, and then if there is a determinant, you can go back to the previous page and see the formula for finding the inverse. So go ahead and find the determinant, and then if the determinant is not 0, find the inverse for example 5. All right, on the next page, we're looking at another square matrix, and we still want to find the determinant, and if there's a determinant, to find the inverse, okay? And the way we can do this is we can use a calculator. So looking again at our calculator, the first thing you want to do is input your matrix. So second, the inverse button, which says matrix above it. And then you want to edit, and we'll edit matrix A. I'm going to make sure that it's a square matrix, 3 by 3. So in our example, it's a 3 by 3 matrix. And then enter in each of those elements. So 1, and then enter, 2, enter, -1, enter, all the way until my matrix is filled out. And then second, quit. And these instructions were in 7.1's notes. So if you want to go back and refresh on how to do that, you can. Okay, and now we actually want to use that matrix. So this is the new part. You're going to do second matrix, and then go over to math. And the first option is DET. That's for determinant. We want to find the determinant. So we're going to hit enter. And then the determinant of what? So we go back in, second matrix, the determinant of matrix A. Okay, close our parentheses and hit enter. So that was second matrix over to math. Option 1 was determinant. Enter. And then we go back to second matrix. Enter. And then enter again. Okay, so we find that the determinant of matrix B equals -10. All right. Since the determinant is non-zero, we want to find the inverse. So again, we're going to go into our matrix menu using matrix A. And then remember, matrix was above the inverse button. So now we can just say, find the inverse of that matrix, enter, and it will give us our matrix. Now, if we want this in fractions instead of decimals, we can go into the math menu and say display it with fractions instead of decimals, which is the first option. So let's go ahead and do that because, as you know, Math Excel usually wants the answers in fractions. So B inverse equals 1/10, 1/5, -1/2, 1/2, 0, 1/2, 1/10, 1/5, 1/2. And that's it for that problem. The last thing we're going to talk about for this section is the properties of matrices. So remember I said that matrices are not commutative with multiplication. So we're going to summarize those properties. So commutative property for addition, which from here on out I'll just abbreviate with a circled plus sign, is going to be that matrix A plus matrix B equals matrix B plus matrix A. And that is true for all matrices. For multiplication, which I'll be abbreviating with a circled multiplication sign, this does not work most of the time. So it's safest to just assume that it is not commutative, and we have just the special cases, the only special cases that we talked about were for the identity and the inverse. In those cases they are commutative, but all other matrices assume that it does not commute. Okay, and then the associative property of addition, which is if you have matrix A plus matrix B then plus matrix C, that will give you the same result as matrix A plus the quantity of matrix B plus matrix C. And for multiplication it also holds. AB times C is equal to A times BC. Okay. The identity property, which we mentioned earlier, is the addition identity. Just like for addition, our identity is 0, we have a 0 matrix. So if I have A plus the 0 matrix, it will give me A, where 0 matrix is the matrix that's just all zeros. All zeros. And for multiplication, we have our identity matrices. So A times the identity matrix of the same size equals A, and that goes for the identity matrix times A as well. Okay, the inverse property for addition, we would say that if I have a matrix A, I can add -1 times matrix A, and it will give me the 0 matrix. And for multiplication, if I have A times its inverse, that's the same as the inverse times A, which should give me the identity matrix. And remember, this only works if the determinant of matrix A is not 0. So this is another notation for determinant. For the distributive property, first we'll talk about distributive property over addition. So if I have matrix A times matrix B plus matrix C, I can say that's the same as matrix A times matrix B plus matrix A times matrix C. Notice A is in front and A is in front. So that also works if I have matrix A plus B then times matrix C. I can distribute, but C is in back, so C has to be the second factor. Okay, this is not equal to CA plus CB. Those are not equal. Okay, and the last property is the distributive property over subtraction. And that states if I have A times B minus C, it's AB minus AC. And if I add A minus B times C, that's AC minus BC, where all of these are matrices. And again, the order does matter because multiplication is not commutative. All right, so the last thing I want you to do for the notes is to fill in a summary of what you learned from this lesson.